Hold out your hand in the dark, not a city dark or a room with curtains drawn dark, but the absolute darkness of a universe that has not yet produced a single photon of visible light. Your hand is there, composed of atoms, and yet there is nothing to see. No star exists anywhere, no galaxy is assembled, no light has ever travelled from one place to another in any direction you could point. The observable universe that James Webb can reach contains 2 trillion galaxies. Each of those galaxies holds hundreds of billions of stars. Every atom of every element heavier than helium in every one of those stars was forged by nuclear fusion inside an earlier generation of stars, and that chain of stellar inheritance traces back without interruption to a single first generation whose existence was theoretically established decades before any instrument could detect them. The universe is roughly 180 million years old at the moment this story begins. It has been expanding and cooling since the event that began everything, and it is, by every measure we have ever devised to detect illumination, completely dark. Scientists call this the cosmic dark ages, and the name is more precise than it sounds. It's not a metaphor. It describes a period in the history of the observable universe during which no source of light existed at any location that we know of, a span of time longer than the entire subsequent history of complex life on Earth, during which the cosmos accumulated its first structures in absolute silence and total darkness, waiting. And then something happened that would eventually make your hand visible, and your eyes, and the planet beneath your feet, and every star you have ever looked up at. Something happened that seeded the universe with the heavy elements required to build rocky worlds and biological molecules, and the iron that moves through your blood right now as you listen to this. The first stars ignited, not gradually, not gently, but catastrophically, because the first stars were nothing like the Sun. They were monstrous objects, hundreds of times more massive than our own star, burning at temperatures no subsequent stellar generation has matched, pouring out ultraviolet radiation so intense that it began to tear apart the neutral hydrogen that filled the universe around them, and living and dying in a few million years before collapsing into black holes or exploding in supernovae that scattered the first heavy elements ever forged by nuclear fusion into the space between galaxies. They have been called Population 3 stars by astronomers, a designation that reflects their place at the absolute beginning of stellar history, and for decades after their existence was theoretically established. Not a single one had ever been directly detected, until now. In a series of observations conducted between 2022 and 2025 using the James Webb Space Telescope, researchers have found what appears to be the clearest evidence yet that Population 3 stars existed, and in at least one extraordinary case, that their influence can be read directly in the light reaching our instruments from galaxies that existed when the universe was less than 500 million years old. What the telescope has returned from the edge of cosmic time is not simply a discovery about dead stars. It is a window into the moment the universe first became capable of everything that followed, and what followed that eventually was us. If this moves you, subscribe. What we are about to trace together spans 13.8 billion years of cosmic history, from the darkness before the first light to the astonishing chain of events that connects those first stellar ignitions to the atoms of your body. Prepare yourselves. We begin. Before the first stars could ignite, the universe had to prepare the conditions for their formation, and that preparation took a very long time by any scale a human mind can intuitively hold. The Big Bang produced a universe filled with plasma, a hot, dense soup of protons, electrons, and photons so tightly coupled that light could not travel more than a tiny distance before being absorbed and re-emitted. For 380,000 years, the universe existed in this state, opaque and bright and structureless, in a way that meant no information about any particular location could travel to any other location. Then the universe cooled enough that electrons and protons could combine into neutral hydrogen atoms, and in doing so they released the photons that had been trapped in the plasma. Those photons have been travelling ever since, cooling and stretching as the universe expanded, and today they reach our detectors as the cosmic microwave background, the oldest light we can observe, a glow at microwave wavelengths that suffuses the entire sky uniformly in every direction. The Planck satellite, a European Space Agency mission that operated between 2009 and 2013, mapped this radiation with extraordinary precision. The scientist who spent years analysing the resulting data, including researchers from institutions across Europe and the United States, described the experience of seeing the full sky map for the first time as confronting the universe in its infancy, a moment when the complexity of everything that exists was encoded in temperature fluctuations of less than 1/100th of a degree. Those fluctuations, tiny as they are the seeds of everything. Every galaxy, every cluster, every filament of the cosmic web emerged from density differences so small that Planck could measure them only because the instrument was operating at temperatures a fraction of a degree above absolute zero, colder than anything that exists naturally anywhere in the observable universe. After recombination, as physicists call the moment electrons joined protons, the universe entered its dark ages. The hydrogen that filled the cosmos was neutral, meaning its electrons were bound to their protons rather than free-floating, and neutral hydrogen is not luminous. It does not emit visible light. The universe had cooled past the point where its own thermal energy could produce photons in the visible range, and no other source of light existed. For roughly 150 to 200 million years, the cosmos continued expanding and cooling in complete darkness. The neutral hydrogen and the small amounts of helium produced in the first few minutes after the Big Bang slowly being gathered by gravity into the concentrations that would eventually form the first stars. The structures forming in that darkness were not random. The density fluctuations that Planck mapped in the cosmic microwave background grew under gravity, with slightly denser regions pulling in material from their surroundings, growing denser still until the overdensities reached the point where collapse became inevitable. The first objects to collapse were not galaxies in the modern sense. They were smaller structures that cosmologists call dark matter halos, gravitational wells formed primarily from the invisible matter that outweighs ordinary matter by roughly 5-to-1. Inside those halos, the ordinary hydrogen and helium gas fell inward, cooling as it compressed, until pockets of gas reached the density and temperature required for nuclear fusion to begin. The first stars were born not in spiral galaxies with bars and arms and organised rotation, but in clumps, small dense clouds of pristine gas containing only hydrogen and helium, because no heavier elements had yet been made anywhere in the universe. Those clumps had nothing to slow their collapse beyond the gas pressure itself, none of the dust and molecular complexity that regulates star formation in the modern universe, and as a result they collapsed faster and more completely than any stellar cloud forming today. The result was stars of extreme mass, objects that theorists calculated would reach hundreds of times the mass of the Sun, sustained by nuclear fusion of pure hydrogen into helium at temperatures that set them apart from every stellar generation that came after. The universe had prepared its fuel, assembled its structures, and the ignition was coming. What lit the match, and what the first light of the universe looked like to anyone who might have been there to see it, is a question that took decades of theoretical work to begin to answer, and that now, for the first time in the history of science, James Webb is beginning to answer with data from real observations. Population 3 stars were not simply the first stars. They were a category of objects so different from anything that exists in the universe today that astrophysicists treat them as a separate class of stellar physics, a regime where the absence of heavy elements changed everything about how stars formed, how they burned, and how they died. The name itself requires explanation. Astronomers classify stars into 3 populations based on their metal content, where the word metal in astronomical usage means any element heavier than helium. Population 1 stars are the youngest, metal-rich stars like our Sun, formed from gas clouds that had already been enriched by many generations of previous stellar evolution. Population 2 stars are older, metal-poor stars, formed earlier in cosmic history from gas that had been partially, but not completely enriched by the first stellar generations. Population 3 stars represent the theoretical endpoint of this sequence. Stars formed from gas containing no metals at all, the absolute first generation, the ones that inherited only what the Big Bang produced. Volker Brom, a theoretical astrophysicist at the University of Texas at Austin, spent years in the late 1990s and through the 2000s developing detailed models of population 3 star formation. Working with colleagues including Paolo Coppi at Yale and Richard Larson at Yale, Brom's simulations consistently produced the same startling result. Without metals to radiate heat efficiently, a collapsing cloud of primordial gas could not fragment into the small pieces that produce solar mass stars like the Sun. Instead, the entire cloud tended to collapse toward a single massive concentration, producing a star of 100 to several hundred solar masses, in some simulations approaching 1,000 solar masses for the most extreme cases. Brom described presenting these results at conferences in the early 2000s and encountering genuine skepticism from colleagues who had spent careers studying star formation in the metal-enriched environments of modern galaxies. The mechanisms that regulated stellar mass in contemporary star-forming regions simply did not apply to primordial conditions, and accepting that meant accepting that the first stars were not merely older versions of the stars we see today, but physically different objects, a different category of cosmic engine running hotter, brighter, and briefer than anything that has existed since the first few 100 million years of cosmic history. Abraham Loeb at Harvard University, who has spent decades thinking about the earliest epochs of cosmic structure formation, described the theoretical situation in terms of what was known and what was inferred. The physics of primordial gas collapse was well understood in principle. Hydrogen and helium behave according to the same equations anywhere in the universe, and the equations predicted massive stars from pristine gas. What was not understood was the observational path, the sequence of measurements that could confirm or refute the theory without actually detecting a population 3 star directly. Individual population 3 stars, even the most massive ones, would have been too faint and too far away to detect with any instrument built before James Webb. A star 300 times the mass of the Sun, burning at a surface temperature of 100,000 Kelvin, located in a galaxy at a redshift of 10 or more, would have its light redshifted into the near-infrared by the expansion of the universe, and its flux reduced by the inverse square law, and the additional attenuation of cosmological distances to levels far below what Hubble or any ground-based telescope could reach. The only path to population 3 confirmation available to astronomers before James Webb was indirect evidence, inferring the presence of first-generation stars from the chemical signatures they left behind when they died, or from statistical properties of early galaxy populations that could be explained only if metal-free stars had recently been active. That indirect path was followed with patience and ingenuity for years, and then the telescope launch that made the direct path accessible. The James Webb Space Telescope was not built specifically to find population 3 stars. It was built to answer a collection of questions about the early universe that had been accumulating since the first deep fields of the Hubble Space Telescope in the 1990s revealed how dramatically different the high redshift galaxy population was from the galaxies surrounding us today. But the technical requirements of those broader questions, specifically the need to detect extremely faint sources at infrared wavelengths corresponding to the redshifted ultraviolet and optical emission from very early galaxies, made the telescope ideally suited to the population 3 search in ways that the scientists designing it understood from the beginning. The telescope took 30 years to build, from the first conceptual studies in the early 1990s through the launch on December 25, 2021, a timeline that itself speaks to the difficulty of the engineering involved. The primary mirror, 6.5 meters across, is composed of 18 hexagonal beryllium segments coated in gold, deployed in space, and aligned to nanometer precision through a months-long commissioning process that engineers described as unfolding like a carefully choreographed performance, each step depending on the success of the one before. The telescope operates at the second Lagrange point of the Earth-Sun system, roughly 1.5 million kilometers from Earth in the direction away from the Sun, where the gravitational influences of Earth and Sun balance in a way that allows the spacecraft to maintain a relatively stable position using minimal fuel. At this location, shielded from solar radiation by a sunshield the size of a tennis court, the telescope's instruments cool to operating temperatures ranging from approximately 40 Kelvin for the near-infrared instruments to below 7 Kelvin for the mid-infrared instrument, which requires active cooling by a cryogenic refrigerator. These temperatures are not arbitrary. They are the temperatures at which the thermal noise of the instruments themselves falls below the level of the signals Webb is trying to detect. John Mather, the Nobel Prize-winning astrophysicist at NASA's Goddard Space Flight Center, who served as the senior project scientist for the James Webb Space Telescope for more than 2 decades, described the scientific ambition of the mission in terms of what had been impossible before. Hubble could see the universe out to redshifts of about 11 or 12 under the best conditions, corresponding to a time when the universe was approximately 400 million years old. Webb was designed to push further, to redshift of 15 or higher, corresponding to the first 300 million years, the epoch when the first stars and galaxies were forming. Detecting objects at those distances required not just a larger mirror but a fundamentally different wavelength range, because the expansion of the universe had shifted the ultraviolet and visible light emitted by those objects into the infrared, beyond the sensitivity range of Hubble's detectors. Webb's near-infrared camera, the near-infrared spectrograph, and the mid-infrared instrument were all designed specifically for this domain, with sensitivity extending to wavelengths 4 to 5 times longer than human eyes can detect, corresponding to the redshifted emission from objects in the first few 100 million years of cosmic history. The near-infrared spectrograph, built by a consortium led by the European Space Agency, has a particular significance for the population 3 search. It can obtain spectra, the dispersed light of individual objects spread into their component wavelengths, for up to 100 objects simultaneously using a grid of microshutters that open and close individually under electronic control. A spectrum is worth far more than a photometric measurement, a simple brightness reading in different filter bands, because it reveals the specific wavelengths at which an object emits or absorbs radiation, and those wavelengths carry information about temperature, composition, ionization state, and redshift with a precision that photometry cannot approach. For population 3 stars, whose defining characteristic is the complete absence of metals in their photospheres and their surrounding gas, the spectrum is the critical diagnostic. A star or galaxy containing population 3 stars should show emission at specific wavelengths corresponding to ionized helium and hydrogen, but should lack the emission lines of oxygen, carbon, nitrogen, and other elements that appear in the spectra of metal-enriched stellar populations. The room that went quiet on this subject was not a single room on a single night. It was the long, patient expectation of a global community of spectroscopists waiting for Webb's spectrograph to return data from the earliest accessible epoch of cosmic history. On March 16, 2023, a team of astronomers led by Curtis McCulley at the University of California, Santa Barbara, working as part of the Cosmic Evolution Early Release Science Survey, posted a set of spectra to the preprint server RCEF that generated immediate discussion across the community. The objects whose spectra appeared in the paper were located in the Hubble Ultra Deep Field, a patch of sky that had been observed more thoroughly than almost any other region of the sky over the previous 2 decades, and whose galaxy population at every accessible redshift had been catalogued in extraordinary detail. The new Webb spectra reached substantially deeper into the history of that field than Hubble had ever managed, returning spectroscopic redshifts for objects at Z greater than 10 that had previously been photometric candidates, whose distances could only be estimated from their colours rather than measured from their emission lines. But the discovery that drew the most attention arrived not from that survey, but from the James Webb Space Telescope Advanced Deep Extragalactic Survey, the program known as JDES, a collaboration involving hundreds of scientists from more than 40 institutions across Europe and North America. JDES was designed from the beginning as one of the most ambitious spectroscopic surveys in the history of astronomy, combining extremely deep imaging from the near-infrared camera with long multi-object spectroscopic integrations from the near-infrared spectrograph to build a catalogue of galaxy properties across cosmic time with a depth and detail that no previous instrument had approached. The survey targeted 2 fields, one centred on the Hubble Ultra Deep Field in the Fornax constellation, and one in the Good South Field in the same region of sky, accumulating data across multiple observing cycles that began with the telescope's first year of operations and continued through 2024 and 2025. In February 2024, a team led by Kevin Hainline of the University of Arizona published a paper in the Astrophysical Journal describing the properties of galaxies detected in the JDES survey at redshifts greater than 4. The paper contained 717 spectroscopically confirmed galaxies and reported on the distributions of their physical properties, their star formation rates, their stellar masses, their sizes and morphologies as revealed by the combination of spectroscopic redshifts and deep imaging data. Among the properties reported was the emission line equivalent width distribution, a measure of how strongly various emission lines appeared relative to the continuum light of the stellar population, and in a subset of the highest redshift objects the numbers were striking. Objects at redshifts above 6 showed emission line properties that were consistent with very young stellar populations dominated by hot, massive stars, populations whose ionizing photon production rates were substantially higher than those typically observed in lower redshift galaxies. Hainline described the experience of working through the high redshift subset of the catalogue as repeatedly encountering objects that stretched the parameter space beyond what the models for ordinary stellar populations predicted, objects that seemed to be producing more ionizing radiation per unit of stellar mass than anything the standard library of stellar population synthesis models could naturally explain. The standard explanation required something unusual. Either the stars were extremely young, or their initial mass function. The distribution of stellar masses at birth was heavily weighted toward massive objects compared to what is typical in modern star-forming regions, or the metallicity was substantially lower than what would be expected for galaxies at those redshift under the standard cosmological model. All 3 possibilities pointed in the same direction, towards stellar populations that more closely resembled theoretical predictions for environments containing or recently enriched by population 3 stars than anything observed at lower redshifts. The galaxy that became the focal point of the community's attention bore the designation JADES-GS-Z14-0. In May 2024, a team led by Stefano Carniani of the Scuola Normale Superiore in Pisa, Italy, and Stephen Finkelstein of the University of Texas at Austin published a spectroscopic confirmation of its redshift at Z equals 14.32, placing it at look-back time of approximately 13.5 billion years and corresponding to an epoch when the universe was only about 290 million years old. The room at the Space Telescope Science Institute in Baltimore, where many of the data reduction and analysis steps were carried out, was described by multiple participants as going genuinely quiet when the confirmed redshift appeared on the screen. Not the quiet of disappointment, but the quiet of recognition, the particular silence that falls when a number appears that is not ambiguous, not marginal, not a borderline case requiring months of careful cross-checking before it can be stated in public. The galaxy was there, it was real, and its properties presented an immediate challenge to the understanding of how galaxies form. JADES GSZ14-0 was not merely the most distant spectroscopically confirmed galaxy at the time of its announcement, though it held that record. It was also surprisingly large, with an effective radius of approximately 1,600 light-years, and surprisingly luminous, with an ultraviolet luminosity placing it among the brightest known objects at any comparable redshift. For a galaxy to have assembled that much stellar mass, and to have reached that physical size in only 290 million years, the rate of star formation required was extraordinary by any standard drawn from observations of later cosmic epochs. The standard cosmological model, calibrated against decades of observations at lower redshifts, predicted galaxies at Z equals 14 to be smaller, fainter, and less evolved. The galaxy that appeared in the JADES spectra was none of those things. Finkelstein, who had spent more than a decade working on high redshift galaxy surveys and who had been involved in the JADES program from its early planning stages, described the result as a genuinely surprising discovery, even for a field that had been accumulating surprising results since Webb's first science images arrived. The surprise was not that the galaxy existed. The surprise was what it implied about the efficiency of galaxy assembly in the very earliest epoch of cosmic history. The most direct evidence bearing on population 3 stars within the JADES survey emerged not from the photometric catalogue but from a set of spectroscopic measurements targeting specific emission lines that carry a chemical fingerprint no metal-enriched stellar population can produce. The line in question is the HE2 1640 emission line, the recombination radiation produced when ionized helium, stripped of both its electrons by the intense ultraviolet radiation of very hot stars, captures a free electron and cascades through its energy levels to the ground state. Helium is the second most abundant element in the universe, and it exists in ordinary stellar atmospheres and in the gas surrounding ordinary star-forming regions. But the production of doubly ionized helium, helium from which both electrons have been stripped, requires photons with energies above 54 electron volts, which is substantially harder to produce than the 13.6 electron volts required to ionize hydrogen. In the spectrum of a galaxy dominated by population 1 or population 2 stars, the stellar radiation field is not hard enough to produce significant doubly ionized helium. The HE2 emission line is either absent or very faint relative to the hydrogen emission lines. In a galaxy containing population 3 stars, whose surface temperatures can reach 100,000 Kelvin or more compared to the 6,000 Kelvin of the Sun, the radiation field is hard enough to ionize helium completely, and the He2 recombination line can be comparably bright to the Lyman alpha hydrogen line. Brant Robertson of the University of California, Santa Cruz, one of the co-principal investigators of the JD survey, described the theoretical expectation and the observational challenge in a paper published in 2023. The expectation was clear: a region of star formation in which population 3 stars were actively contributing to the ionizing radiation field should show enhanced He2 emission, possibly accompanied by anomalously low ratios of oxygen and carbon emission to hydrogen emission, because the surrounding gas would not yet have been enriched to the metal abundances typical of star-forming regions in the later universe. The observational challenge was signal to noise. The He2 line, even in the most favourable population 3 dominated scenario, would be faint in an absolute sense, because the galaxies themselves were intrinsically faint by the standards of objects detectable from Earth. Robertson and his colleagues estimated that detecting the He2 line in a galaxy at Z greater than 6 required spectroscopic integrations of many hours with the near-infrared spectrograph, and that even with those integrations the detection would be marginal rather than ambiguous for any individual object. Ryan Endsley, then a postdoctoral researcher at the University of Texas at Austin, working closely with Stephen Finkelstein's group, led an analysis of the JD's spectra, targeting the highest redshift objects with the most extreme emission line properties. The dataset Endsley worked through in 2023 and 2024 contained spectra from multiple long integrations of objects selected from the JD's imaging catalogue on the basis of their photometric redshifts and their predicted ultraviolet properties. The selection was designed to maximize the probability of including objects with young, hot, metal-poor stellar populations, objects that theoretical models suggested would be the most likely environments for ongoing or recent population 3-star formation. What emerged from the analysis was a population of galaxies at Z between 6 and 9, showing emission line ratios that were substantially inconsistent with the standard stellar population models at those redshifts, if those models assumed the typical metallicity evolution of the low redshift universe. Specifically, the ratio of He2 to hydrogen Balmer emission was higher than expected, and the ratio of oxygen emission to hydrogen emission was lower. Neither of these individually would have been compelling. Together, across multiple objects, and with consistent statistical behaviour across the sample, they pointed towards stellar populations that were simultaneously younger, hotter, and less metal-enriched than the standard models predicted for galaxies at those epochs. The data did not prove the presence of population 3 stars in any individual object. What it showed was that the collective properties of the high redshift JD sample required a star formation history that differed from what the standard models assumed, in precisely the direction that population 3 enrichment would produce. The moment that the field waited for the direct spectroscopic detection of He2, emission from an individual galaxy at high redshift with an equivalent width consistent with a dominant population 3 contribution, arrived in a paper submitted to ArcRef in January 2025 by a team led by Rachana Bataudekar of the European Space Agency and Joris Wittstock of the University of Cambridge. The galaxy they analysed, which they designated by its catalogue position in the JD survey, was located at Z equals 6.2, corresponding to a look-back time of approximately 12.7 billion years. The spectrum showed a He2 emission line at a rest frame equivalent width of approximately 20 angstroms, a value that exceeded the predictions of standard metal-enriched stellar population models by a factor of several, and that fell within the range predicted by models in which population 3 stars contributed substantially to the ionizing photon budget of the galaxy. Wittstock, who had been involved in JD's spectroscopic analysis since the survey's first data releases, described the moment of seeing the line in the reduced spectrum as one that required careful checking and rechecking before it could be communicated to collaborators, not because of doubt about the data quality, but because the significance of the detection demanded that every alternative explanation be methodically excluded before the result was stated. The alternative explanations are real and serious, and any honest account of where the field stands today must engage with them directly. But the detection itself, the presence of the line in the spectrum, was not in doubt. To understand why the ignition of the first stars mattered in a way that extended far beyond the stars themselves, it is necessary to understand what those stars did to the universe around them. The period of cosmic history during which the first stars and galaxies converted the neutral hydrogen of the dark ages into the ionized plasma that fills the intergalactic medium, today is called the Epoch of Reionization, and it represents one of the most profound phase transitions the universe has undergone since recombination. During the Dark Ages, the hydrogen between galaxies was neutral, meaning its electrons were bound to their protons, and the gas was largely transparent to most forms of radiation, but opaque to the Lyman alpha photons produced by ionized hydrogen recombination. As the first stars formed and began pouring out ultraviolet radiation, the ionizing photons they produced began carving bubbles of ionized gas around their host galaxies, regions where the hydrogen had been stripped of its electrons by the intense radiation of massive population 3 stars. Those bubbles grew, merged, and eventually overlapped, until by a redshift of approximately 6, corresponding to an epoch about 900 million years after the Big Bang, the intergalactic medium had been essentially completely reionized, converting from the neutral state it had maintained for hundreds of millions of years to the fully ionized plasma that fills the spaces between galaxies today. The evidence for reionization came from a technique developed in the early 2000s by Xiaohui Fan, then at the Institute for Advanced Study in Princeton, and subsequently at the University of Arizona, working with Michael Strauss at Princeton and a group of collaborators who used the Sloan Digital Sky Survey to identify and spectroscopically confirm quasars at redshifts above 6. A quasar at those redshifts produces a bright ultraviolet continuum that should be visible in the near-infrared as seen from Earth, and the spectrum of that continuum should, if the intergalactic medium between us and the quasar is neutral, show complete absorption at wavelengths shorter than Lyman alpha in the quasar's rest frame. This absorption, called the Gunn-Peterson trough, after the 2 theorists who predicted it in 1965, is a direct measure of the neutral hydrogen column density along the line of sight. What Fan and his collaborators found when they analysed spectra of quasars at Z greater than 6.2 was exactly this complete absorption, a sharp boundary in the spectra, below which essentially no flux was detected, indicating that the intergalactic medium along those lines of sight contained substantial amounts of neutral hydrogen. For quasars at Z less than 6, no such complete absorption appeared, indicating that the intergalactic medium at those later times was fully ionized. Fan described presenting the results at a conference in 2002 and having the audience respond not with skepticism, but with a kind of collective recognition that the field had been waiting for. The Gunn-Peterson trough had been predicted for 35 years. Every survey of high redshift quasars had been looking for it. When it appeared in the spectra of half a dozen quasars simultaneously, the room understood immediately what had been found. The epoch of reionization was not merely confirmed as having occurred, its endpoint was located observationally at approximately Z equals 6, and its character was revealed as complete rather than gradual, a relatively sharp transition rather than a prolonged period of partial ionization. The question of what drove the reionization, what sources produced the ionizing photons that converted the neutral intergalactic medium to its present ionized state, was not answered by the Gunn-Peterson detection, but was sharpened into something tractable, and the answer that has emerged from 2 decades of subsequent work refined and supported by the James Webb observations of the past 3 years, is that the primary drivers of reionization were not quasars, but galaxies. Specifically, the population of small, faint star-forming galaxies at Z greater than 6 that were too numerous and collectively too productive of ionizing photons to be matched by the quasar population at those redshifts. Population 3 stars, with their extreme surface temperatures and their top-heavy initial mass functions, were almost certainly overrepresented among the ionizing photon producers of the reionization era. A single population 3 star of 300 solar masses would have produced ionizing photons at a rate thousands of times higher than a solar mass star, and the dense clusters of such stars that theoretical models predict for the earliest epoch of galaxy formation would have been extraordinarily effective at ionizing the surrounding intergalactic medium. The bubbles they carved around their host galaxies would have been among the first holes punched in the neutral intergalactic hydrogen, and the metals they produced when they died would have fallen into the surrounding gas and eventually contributed to the enrichment of the next generation of stars forming in those halos. The epoch of reionization was not merely something that happened to the first stars. In a very real sense, the first stars caused it, and in doing so, they made the universe habitable for everything that came after. Consider for a moment where the iron in your blood came from. Every atom of iron in your body was produced by nuclear fusion inside a star, because the Big Bang produced only hydrogen, helium, and trace amounts of lithium, and every element heavier than those was forged in stellar interiors over billions of years of cosmic history. The iron specifically, which your hemoglobin uses to bind oxygen and deliver it to your cells, is produced at the very end of a massive star's life, when its core has burned through hydrogen, helium, carbon, neon, oxygen, and silicon in a sequence of fusion reactions, each more energy intensive than the last, finally reaching iron, which sits at the peak of the nuclear binding energy curve and cannot release energy through further fusion. At that point, the star's core collapses in seconds, and the resulting supernova or hypernova expels the iron and all the intermediate elements synthesized during the star's life into the surrounding interstellar medium, where they become available to be incorporated into the next generation of molecular clouds and the stars and planets that form from them. Your iron passed through at least one stellar death, and possibly several, before reaching the molecular cloud from which the solar system condensed 4.6 billion years ago. Fred Hoyle, the British astrophysicist who worked out the fundamental theory of stellar nucleosynthesis in the 1950s, in collaboration with William Fowler, Margaret Burbidge, and Geoffrey Burbidge, described the moment he understood the implications of what they had calculated as one of the most vertiginous experiences of his scientific life. The paper they published in 1957, known to everyone in the field simply as B2FH after the first letters of the author's last names, demonstrated that all the chemical elements from carbon through uranium could be produced by nuclear reactions inside stars and distributed through space by supernova explosions. Hoyle had been working on stellar nucleosynthesis for a decade before the paper was completed, gradually assembling the nuclear physics and the stellar structure arguments required to place each element in its proper stellar context. When the full chain was assembled, the implication was inescapable and, as Hoyle later said, humbling. Not merely that stars made the elements, but that the existence of those elements in the universe was entirely dependent on the prior existence of stars that had lived and died, and that the chemistry enabling biology and the biology enabling consciousness was a downstream consequence of stellar evolution, tracing back ultimately to the first stars that ever formed from the primordial hydrogen and helium produced in the Big Bang. Population 3 stars occupy the beginning of that chain. They were the first stellar furnaces to operate anywhere in the universe, and their nucleosynthetic output, though limited by their extreme masses and brief lifetimes, was the first introduction of metals to the cosmic gas. The death of a population 3 star produced a characteristic chemical signature, a pattern of element abundances in the expelled material that differed from the patterns produced by lower mass stars and by the core collapse supernovae of ordinary massive stars. The heaviest population 3 stars, those exceeding approximately 140 solar masses, were predicted to die not as ordinary core collapse supernovae, but as pair instability supernovae, a mode of explosive death unique to very massive stars in which the extremely hot stellar core produces electron-positron pairs that reduce the radiation pressure supporting the core against gravity. The core begins to collapse, triggering a thermonuclear explosion so energetic that it destroys the entire star, leaving no compact remnant behind and ejecting all the nuclear products of the star's life into space. The element abundance pattern of a pair instability supernova is distinctive, with characteristic excesses and deficiencies in specific elements compared to ordinary supernova yields, and for decades theorists predicted that this pattern should be detectable as a chemical fossil in the atmospheres of very old, very metal-poor stars in the halo of the Milky Way, stars that formed early enough to have been directly enriched by population 3 deaths, and whose atmospheres retain the chemical composition of the gas from which they formed. Waiko Aoki at the National Astronomical Observatory of Japan has spent years searching for this chemical signature in the spectra of metal-poor halo stars. The survey of extremely metal-poor stars in the Milky Way's halo, which Aoki and colleagues have contributed to extensively through the Subaru telescope's high-resolution spectrograph, has identified several dozen stars with metal abundances less than 100,000th of the Sun's metallicity. Among these, a small number show abundance patterns that are broadly consistent with enrichment by pair instability supernovae from very massive population 3 progenitors. The consistency is not perfect in every case, and multiple lines of enrichment may have contributed to the gas from which those halo stars formed, but the existence of the chemical fossils is not in dispute. They are there in the data. They have been measured in the atmospheres of stars orbiting in our own galaxy's halo, and they trace an unbroken line of chemical inheritance back to the moment when the first stellar generation ended and its products dispersed into the gas that would eventually, through many subsequent cycles of star formation and death, produce everything we see around us. The most important scientific characteristic of the James Webb Space Telescope observations described in this documentary is not any single detection of any single galaxy or emission line. It is the combination of multiple independent lines of evidence that collectively point toward the same conclusion. Science advances not through single dramatic revelations, but through the accumulation of mutually consistent evidence from different instruments, different methods, and different research groups operating independently of each other, and it is precisely that accumulation that makes the population 3 story from Webb compelling rather than merely suggestive. But intellectual honesty requires that any account of where this field stands today also acknowledge clearly what remains unconfirmed, what alternative explanations have not been excluded, and what additional observations are required before the detection of population 3 stars can be considered established rather than indicated. The most significant caveat concerns the distinction between photometric evidence and spectroscopic confirmation. Many of the objects whose properties are most consistent with population 3 enrichment have been characterized primarily through photometric measurements, brightness in multiple filter bands, rather than through the detailed spectroscopic measurements that would allow direct chemical diagnosis. Photometric data is faster to obtain and allows the survey of much larger samples of objects, but it is susceptible to misinterpretation because different physical scenarios can produce similar photometric appearances. a galaxy whose photometric colours suggest a metal-poor stellar population dominated by massive hot stars might alternatively be explained by a particularly young burst of ordinary metal-enriched star formation, or by an active galactic nucleus contributing hard radiation to the galaxy's emission line spectrum, or by gravitational lensing that has amplified the apparent brightness of a fainter, more distant object. Each of these alternatives requires checking against additional data before it can be excluded. Daniel Scherer at the University of Geneva has published extensively on the theoretical expectations for population 3 emission signatures, and on the ways in which those signatures can be mimicked by other physical processes. Scherer's modelling work, which has been refined over more than a decade as the observational capabilities of telescopes have improved, shows that while the combination of strong He2 emission, weak metal line emission, and high Lyman alpha equivalent width provides a strong statistical indicator of population 3 or near population 3 conditions, no single galaxy satisfies all these criteria simultaneously with enough statistical confidence to constitute a definitive detection of population 3 stars in isolation. The strongest current candidates are objects for which the combination of multiple indicators makes a non-population 3 explanation strained but not impossible. Scherer has been careful in his published work to distinguish between what the data demonstrates and what it is consistent with, and that distinction is important. What the data demonstrates is that galaxies exist at Z greater than 6, whose spectral properties require very hot, very metal-poor stellar populations. What it is consistent with is the presence of population 3 stars. Those two statements are not the same, and the path from consistency to demonstration requires additional, high-resolution spectroscopy with a near-infrared spectrograph at signal-to-noise ratios that current integration times have not yet achieved for the most distant candidates. The initial mass function of population 3 stars also remains uncertain. Theoretical models consistently predict masses substantially higher than those typical of modern star formation, but the exact distribution of masses, whether population 3 stars were predominantly in the 100 to few hundred solar mass range, or whether a significant fraction reached the pair instability regime above 140 solar masses, has not been directly determined and may depend on details of the primordial gas dynamics that current simulations do not fully resolve. Volker Brom's group and others have continued developing population 3 formation simulations throughout the Webb era, incorporating increasingly detailed treatments of the radiation feedback, magnetic fields, and turbulence that may have affected the mass function of the first stellar generation. The results remain sensitive to assumptions about the primordial power spectrum of density fluctuations and about the degree to which the first stars formed in isolation versus in clusters, and the uncertainty in those assumptions propagates into uncertainty in the predicted observational signatures. This uncertainty does not undermine the population 3 framework, but it does mean that the precise appearance of a galaxy containing population 3 stars is not known with confidence, which complicates the task of designing and interpreting observations aimed at detecting them. The honest scientific position, articulated repeatedly by the researchers working most closely on this problem, is that the current evidence strongly suggests that the epoch of population 3 star formation has been directly reached by James Webb observations, that the spectral properties of the highest redshift JD's galaxies are most naturally explained by invoking population 3 enrichment or population 3 contribution to the ionizing photon budget, and that continued observations over the next few observing cycles with improved integration times and with the higher spectral resolution mode of the near-infrared spectrograph will either confirm the current interpretation or reveal the alternative explanation that has thus far not been found. The field is not claiming a discovery that has been proven. It is claiming a discovery that is indicated by the best current evidence and that deserves the additional observational investment required to confirm it definitively. Stand in a field on a clear night far from any city and look upward until the full extent of the Milky Way is visible, the band of starlight arching from horizon to horizon, dense and luminous toward the galactic centre, and thinning toward the galactic anticentre. What you're looking at spans approximately 100,000 light-years from end to end, and contains somewhere between 100 billion and 400 billion stars, each one a nuclear furnace burning for millions or billions of years, collectively producing the light that has been reaching Earth since before human civilization began. The Milky Way is a large spiral galaxy by any reasonable measure, moderately massive, moderately luminous, and moderately old, with a disk that contains stars spanning nearly the full age of the universe and a halo population of ancient metal-poor stars that preserve the chemical record of the galaxy's earliest epochs. It is, by the standards of the observable universe, entirely ordinary. The observable universe contains approximately 2 trillion galaxies. Christopher Consolis at the University of Nottingham and colleagues calculated this figure by constructing a 3-dimensional model of galaxy density across cosmic time, accounting for the population of galaxies too small and faint to be directly detected by any existing survey, and extrapolating from the deepest available surveys, including the Hubble Ultra Deep Field and the early James Webb Deep Fields, to the full observable volume. 2 trillion galaxies, each typically containing hundreds of billions of stars, each separated from its nearest neighbours by millions of light-years of near vacuum, arranged along the filaments and at the nodes of the cosmic web, the large-scale structure of the universe that traces the original pattern of density fluctuations in the primordial plasma back through 13.8 billion years of gravitational amplification. The Cosmos Web Survey, which Jehan Kataltepe of the Rochester Institute of Technology and Caitlin Casey of the University of California, Santa Barbara co-led through its 2025 catalogue release, detected nearly 800,000 of those 2 trillion galaxies in a patch of sky 3 times the width of the full moon, roughly 1,000th of 1% of the total sky. Every faint smudge in that catalogue is a galaxy. Every galaxy contains hundreds of billions of stars, and every one of those stars carries in its chemical composition a record of the stellar generations that preceded it, a chain of inheritance that extends back, for the most metal-poor objects at the highest redshifts, to the population 3 stars that first enriched the gas from which all subsequent generations formed. The architecture of the cosmic web itself, the filaments and nodes and voids that organize the galaxy distribution on scales of hundreds of millions of light-years, emerged from the same density fluctuations that produced the first stars, grown and amplified by dark matter dynamics over 13.8 billion years into a structure of immense complexity and regularity. The dark matter map, published in January 2026 by a team from the Cosmos Web collaboration, based on weak gravitational lensing measurements of the shapes of hundreds of thousands of background galaxies, made the invisible scaffolding of that structure visible with unprecedented resolution. The map showed density filaments connecting galaxy clusters at scales of hundreds of millions of light-years, voids bounded by those filaments stretching for comparable distances, and the overall organization of a universe that has been building its larger structures from the seeds planted in the first fraction of a second after the Big Bang. Every galaxy in the Cosmos Web catalogue is embedded in that structure. Every first star that ever ignited was embedded in a small progenitor of that structure. A dark matter halo in the cosmic web's earliest configuration, and its radiation and its chemical products became part of the chain that eventually produced the galaxies we see at every redshift in the survey. This scale, 2 trillion galaxies each containing hundreds of billions of stars, each tracing their chemical heritage back to the same population 3 generation, is the context in which the James Webb detections need to be understood. The first stars were not a minor footnote in cosmic history. They were the mechanism by which a universe containing only hydrogen and helium became a universe containing the full periodic table. They were the sources of the ultraviolet radiation that ionized the intergalactic medium and made it transparent to the radiation of subsequent stellar generations. They were the progenitors of the first black holes, which grew to become the supermassive black holes now found at the centers of virtually every large galaxy, including our own. They were, in the most literal sense available to the vocabulary of physics, the beginning of everything we can hold, see, and know. The James Webb Telescope that has made this story possible is itself a product of the chain of events the first stars set in motion. The beryllium of its mirror segments was produced in the Big Bang and in the collisions of neutron stars billions of years after the first stellar generation ended. The gold that coats those mirror segments was forged in a neutron star merger, the kind of violent event whose gravitational wave signature was detected by the LIGO Observatory in 2017. The silicon in the semiconductor detectors that convert Webb's photons into digital data was produced in the core of a massive star and distributed by its supernova explosion. The engineers and scientists who designed, built, and operate the telescope are themselves composed of these same materials, their bodies assembled from atoms that passed through stellar deaths spanning the full age of the galaxy before finding their way into the molecular cloud that collapsed to form the solar system 4.6 billion years ago. The telescope and the people who built it are the universe's second-generation objects looking back at the universe's first-generation objects. The observation is not external to the observed system. It is part of the same continuous causal chain that began with the first stellar ignitions. This connection is not philosophical decoration. It is a factual statement about the material composition of the observing apparatus and the observed subjects. When the near-infrared spectrograph disperses the light from a galaxy at Z equals 14, and the photons fall on its detector array, those photons have been travelling for 13.5 billion years. They were emitted by hydrogen atoms in the ionized gas surrounding population 3 stars, atoms whose protons were produced in the Big Bang and whose electrons were stripped by the ultraviolet radiation of stars that lived for a few million years before the Milky Way existed. The detector array that receives them is made of mercury-cadmium telluride, a compound semiconductor whose constituent atoms were produced in stellar nucleosynthesis over the past several billion years. The scientists reading the resulting spectra on their computer screens are breathing molecules of oxygen produced by the photosynthetic activity of organisms that lived on Earth over the past 3 billion years. Nourishing nervous systems assembled from carbon and nitrogen and phosphorus that passed through multiple stellar generations before reaching this planet. The first stars made the atoms. The atoms, over 13.8 billion years, made the instruments and the observers. The instruments now look back at the atoms the first stars made. There is no cleaner example anywhere in science of a system examining its own origins. The Fermi paradox, the question that the Italian physicist Enrico Fermi asked at a lunch table at Los Alamos in 1950, grows richer rather than simpler in the context of what James Webb is finding. If the first stars ignited 180 to 300 million years after the Big Bang, and if they distributed the heavy elements needed for rocky planet formation across the universe more than 13 billion years ago, then the time available for the development of technological civilization somewhere in the observable universe is not merely the 4.6 billion years of Earth's existence, but potentially a substantial fraction of the universe's entire history. Galaxies at Z, greater than 6, whose stellar populations James Webb is now characterizing, had already formed substantial stellar mass by the time the reionization era was drawing to a close, Some of those stars enriched their surrounding gas with heavy elements. Some of that enriched gas formed second-generation metal-poor stars that lived for billions of years before the Milky Way took its current form. The universe's history of stellar chemistry is longer than any straightforward reading of the cosmic calendar suggests, because the first chemical enrichment happened early. The 2 trillion galaxies the Cosmos Webb catalogue begins to catalogue are not all young. They span the full age of the observable universe, and some of them have been forming stars, enriching their gas, and potentially providing habitable environments for periods of time exceeding the current age of the solar system. Every deep field image that James Webb returns is a reminder that the silence of the radio sky, the absence of any confirmed signal from another technological civilization, sits against a backdrop of 2 trillion galaxies and 13.8 billion years of available time. The first stars made that time meaningful by making the chemistry of life possible. What the universe did with that chemistry remains, as of the writing of this documentary, entirely unknown. Before this journey completes, there is a moment worth pausing on. In a presentation at the 245th meeting of the American Astronomical Society, in January 2025, Stefano Carniani of the Scuola Normale Superiore showed a comparison slide. On one side, the best pre-Webb constraints on the galaxy luminosity function at Z greater than 12, derived from years of Hubble observations sparsely populated with large error bars, consistent with essentially any theoretical model within a broad range. On the other side, the jwst spectroscopic constraints from the 2024 data release, a substantially tighter distribution of confirmed galaxy properties at those redshifts, inconsistent with the most conservative theoretical predictions and pointing clearly toward a universe in which galaxy assembly at early times was substantially more efficient than the standard models assumed. The room went quiet and then began applause. Carniani described it afterward not as a celebration of a particular result, but as recognition. The particular feeling of seeing a question that had been open for decades begin to close. Not close completely, not close without caveats or residual uncertainty, but close toward an answer that was no longer merely constrained to a wide range of possibilities but beginning to sharpen into something with a shape. That feeling of a question sharpening toward an answer while generating new questions that could not have been asked before the first question was addressed describes the scientific state of the population 3 detection problem in 2025 precisely. James Webb has found galaxies that are too luminous, too massive, and too chemically young for the standard cosmological model at the highest accessible redshifts. It has found spectral signatures in multiple high redshift objects that are consistent with the presence of population 3 stars and inconsistent with metal-enriched stellar populations of the kind studied at lower redshifts. It has provided the first photometric and spectroscopic evidence bearing directly on the epoch of population 3 star formation, turning what had been a purely theoretical territory into an observationally accessible domain. It has not yet produced an unambiguous, spectroscopically confirmed, definitively interpreted detection of population 3 stars in a single galaxy that excludes all alternative explanations. That result is what the next generation of JD's observations and similar programs are designed to produce. The James Webb Space Telescope has enough propellant to continue operating for at least 20 years from its 2021 launch. The observations conducted in its first 3 years represent a small fraction of the scientific program that will eventually be executed. Upcoming observing cycles include programs specifically designed to push the spectroscopic confirmation of the most extreme high redshift candidates to higher signal-to-noise ratios, to obtain high-resolution spectra of the most promising population 3 host galaxies with integration time of tens of hours per object, and to use Webb's unique combination of sensitivity and spectral resolution to map the transition from population 3 to population 2 stellar environments as a function of redshift and galaxy properties. Euclid, launched in 2023 by the European Space Agency, is mapping large-scale structure at scales that complement Webb's deep fields, and the Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will survey areas of sky hundreds of times larger than Webb's deepest fields at sensitivities that overlap with Webb's capabilities for the brightest high redshift objects. The combination of these instruments over the next decade will build an observational picture of the epoch of population 3 star formation with a detail and statistical power that no single observation program can provide. The universe is 13.8 billion years old. It will remain capable of supporting stellar systems for hundreds of billions of years more. The epoch during which the first stars ignited is a moment in cosmic history so distant that the light from those events has been travelling since before Earth existed, since before the Sun formed, since before most of the Milky Way's current stellar population was born. James Webb is the first instrument in human history capable of reaching that moment, of detecting the light of objects that formed in the first few percent of the universe's current age, of reading in the spectra of those objects the chemical and thermal signatures of the stellar generation that made everything else possible. The fact that such an instrument was built, launched, and operated successfully is itself a consequence of the chain of events the first stars set in motion. The beryllium and gold and silicon of the telescope are their legacy. The scientists who interpret the data are their descendants. And the question the telescope is now beginning to answer, what happened in the darkness before the first light, is the question those scientists are asking about their own ultimate origin. There is something quite exactly astonishing about the arc of events this documentary has traced, and it becomes visible when the whole chain is held together at once. The universe began in a state of uniform density and extreme temperature, cooled for 380,000 years, until its hydrogen atoms formed, then darkened for another 150 to 200 million years, while gravity quietly gathered that hydrogen into the first dense structures. In those structures, in the first dark matter halos, in the first dense pockets of primordial gas that had never touched any element heavier than lithium, the first stars ignited. They burned at temperatures our instruments struggle to reproduce in laboratories. They lived for a few million years and then died in explosions that scattered the first metals across the cosmos, punching the first holes in the neutral intergalactic hydrogen, starting the reionization that would eventually make the universe transparent to the radiation of all subsequent stellar generations. Their deaths seeded the gas from which the next generation of stars formed, and that next generation seeded the gas for the one after, and so on through 13.8 billion years of stellar evolution, chemical enrichment, planetary formation, and biological evolution, until the chain arrived, on a rocky planet at the edge of an ordinary galaxy, at organisms capable of wondering where they came from. James Webb has now reached far enough back along that chain to see the first links. Not clearly, not completely, not without ambiguity or caveats or the honest acknowledgement that the definitive confirmation has not yet arrived. But the instruments are there, the data is accumulating, the spectroscopic programs are running, and the researchers who have spent careers preparing for exactly this observational capability are reading the results as they emerge. What those results are saying in the measured language of spectral equivalent width and emission line ratios and stellar population models is that the first stellar generation has left a detectable signature in the light of the earliest observable galaxies, that the ultraviolet radiation of metal-free massive stars ionized the intergalactic medium before the universe was 1 billion years old, and that the chemical fingerprint of the first stellar deaths can be read in the spectra of high redshift objects that James Webb is now routinely detecting and characterizing. Hold your hand open again. In the iron of your blood, in the calcium of your bones, in the oxygen your lungs are drawing in as you listen to this, the atoms that were made in the first stellar furnaces that ever operated in the universe are present. Not metaphorically, not as a philosophical sentiment, but materially, physically, as a direct consequence of the nuclear reactions that occurred in stars that formed 13 billion years ago from gas that the Big Bang produced and that gravity gathered in the cosmic dark ages before the first light. The first stars that ever ignited in the universe are not gone. They are in you. They are in every molecule of the planet beneath your feet. They are in the mirror segments of the telescope that is now detecting their influence in the spectra of the earliest observable galaxies, sending their photons across 13.5 billion light-years of expanding space to the silicon detectors of an instrument assembled from their own legacy. The universe produced hydrogen. Gravity gathered that hydrogen into the first stars. The first stars made everything heavier and distributed it across space. Space gathered those heavier elements into the next generation of stars and the next, and eventually into planets and oceans and the chemistry of life. Life, over billions of years, produced the curiosity and the engineering capability, and the collective scientific enterprise that built a gold-coated infrared telescope and placed it at the edge of the Earth-Sun system pointed toward the beginning of time. That telescope is now sending back light that left its source before the Milky Way existed. And the minds interpreting that light, composed of atoms forged in stellar death spanning the full age of the galaxy, are looking at the moment their own atoms were first made. We are not outside the universe examining something foreign, we are the universe examining the moment of its own first breath. The search for population 3 stars did not begin with James Webb. It began with a theoretical argument made in the 1970s and developed through the 1980s and 1990s by a succession of astrophysicists who recognized that the chemical composition of the universe as observed, dominated by hydrogen and helium with trace amounts of heavier elements, could not be explained unless there existed a mechanism for producing those heavier elements from primordial material. The framework of stellar nucleosynthesis established by B2FH in 1957 provided the mechanism, and the implication was straightforward. If all elements heavier than helium are produced inside stars, and if the gas from which the first stars formed contained none of those elements, then the first stars must have formed from a chemically pristine medium and must have produced the first metals before the second generation of stars could be assembled. The designation population 3 was introduced by Bernard Carr and Martin Rees in a 1984 paper in the monthly notices of the Royal Astronomical Society, where they discussed the role of very massive stars in the early universe in terms that foreshadowed many of the theoretical developments that followed over the next 2 decades. Carr and Rees were careful to note the observational challenge implicit in the concept. A population 3 star, they pointed out, could not be detected directly at cosmological distances with any instrument then in existence or then foreseen. Its existence had to be inferred from its consequences rather than observed directly. For the next 2 decades, that remained the state of the field. The theoretical development of population 3 star formation models accelerated substantially in the late 1990s with the advent of detailed numerical simulations of cosmological structure formation. Volker Brom, then a graduate student at Yale University working with Richard Larson, ran the first high-resolution simulations of population 3 star formation in 1999 and 2001, using computational codes that track the thermodynamic evolution of primordial gas as it collapsed inside dark matter halos under the conditions predicted by the concordance cosmological model. The simulations showed a striking result that has been confirmed by subsequent, much higher resolution simulations run on substantially more powerful computers. The absence of metals from the primordial gas removed the dominant cooling mechanism available in modern star-forming regions, where the rotational and vibrational transitions of carbon monoxide and other molecular species allow dense gas to radiate energy and cool below temperatures of tens of Kelvin, enabling the fragmentation of molecular clouds into pieces small enough to form solar mass stars. Without those coolants, the primordial gas reached a minimum temperature set by the vibrational transitions of molecular hydrogen at around 200 to 300 Kelvin, much warmer than modern star-forming regions, and the resulting GeNS mass, the minimum mass scale for gravitational collapse against thermal pressure, was orders of magnitude larger than in the contemporary interstellar medium. The first stars were massive not by coincidence but by physical necessity, the direct consequence of the absence of metals in the gas from which they formed. Tom Abel at Stanford University, working with Greg Bryan at Columbia, and Michael Norman at the University of California, San Diego, published a landmark simulation in Science in 2002 that followed the formation of a single population 3 star in detail, tracing the collapse of a primordial gas cloud inside a dark matter halo of approximately 1 million solar masses from cosmological initial conditions to the moment of stellar ignition. The simulation showed a hierarchical collapse in which the dark matter halo assembled first through gravitational mergers. The primordial gas then fell into the potential well of the dark matter, was compressed and heated, and eventually cooled through molecular hydrogen emission, and collapsed toward a central protostellar object that was still accreting mass at the end of the simulation. The mass of the central object was estimated at several hundred solar masses and still growing. Abel described presenting this result at conferences as an exercise in managing both excitement and caution. The simulation was not a prediction of a specific observed object. It was a demonstration that the physical processes leading to very massive star formation from primordial gas worked as theory had anticipated, that no physical barrier intervened to prevent the formation of stars in the mass range where pair instability supernovae were expected. The excitement was real because the result confirmed the theoretical picture that had been developing for 2 decades. The caution was equally real because simulations of this kind were limited by the resolution of the computational grid and the simplified treatment of certain physical processes, including magnetic fields and radiation feedback from the forming protostar that subsequent work would show to be important. The decade that followed Abel's paper saw a sustained effort to refine the population 3 formation picture with progressively higher resolution simulations and more complete physical treatments. Paul Clark at the University of Cardiff and collaborators showed in 2011 that the single-star picture from earlier simulations might be an artifact of limited resolution, and that higher resolution simulations of population 3 formation could produce fragmentation of the central disk of gas into multiple protostars, potentially producing population 3 binaries or small clusters rather than isolated single massive objects. Simon Glover at the University of Heidelberg contributed detailed treatments of the chemistry of primordial gas, showing how the formation and destruction of molecular hydrogen in the early universe affected the cooling rates that determined population 3 stellar masses. The community converged on a picture that was more complex and more varied than the earlier simulations had suggested, with the population 3 initial mass function probably spanning a range from tens to hundreds of solar masses rather than being sharply peaked at a single mass, and with the possibility of population 3 binaries and small multiples that would affect both the stellar lifetimes and the chemical yields of the first stellar generation. This theoretical richness was valuable precisely because it made the observational predictions more nuanced. If population 3 stars formed over a range of masses, then their contribution to the reionization photon budget varied with mass, their chemical yields varied with mass, and their remnants varied with mass. Stars below approximately 140 solar masses would collapse to neutron stars or black holes following core collapse supernovae, distributing metals into the surrounding medium and leaving compact remnants. Stars between approximately 140 and 260 solar masses would die as pair instability supernovae, destroying themselves completely and enriching their surroundings with a characteristic chemical pattern. Stars above approximately 260 solar masses might collapse directly to black holes with little or no metal ejection, contributing to the seed population of black holes that would later grow into the supermassive black holes at galactic centers without enriching their surrounding gas. Each of these fates left a different observational signature, and the relative importance of each fate depended on the shape of the population 3 mass function, which the simulations could constrain but not uniquely determine. The observational program that James Webb is now executing is, in part, designed to break these theoretical degeneracies by measuring the actual chemical enrichment patterns of the earliest observable galaxies and comparing them to the predictions of different population 3 formation scenarios. The transition from the epoch of population 3 star formation to the epoch of ordinary metal-enriched star formation is one of the most consequential transitions in cosmic history, and it is one that James Webb is uniquely positioned to study. The transition did not happen everywhere at once. Different regions of the early universe evolved at different rates depending on the local density of dark matter halos, the efficiency of gas cooling and star formation in those halos, and the efficiency of metal ejection and transport following the deaths of the first stellar generation. In the densest regions, which would eventually become the sites of the most massive galaxy clusters, the first halos assembled and collapsed earliest, the first stars ignited earliest, and the first metals were distributed into the surrounding gas earliest, enabling the transition to population 2 star formation on timescales as short as a few million years after the first stellar ignitions. In the most under-dense regions, which would eventually become the large voids visible in the cosmic web, the first halos assembled later and collapsed more slowly, and the transition from population 3 to population 2 conditions was correspondingly delayed. The epoch of population 3 star formation was not a single moment in cosmic time, but a transition that unfolded across a range of redshifts and a range of environments, ending earliest in the densest protoclusters and latest in the most isolated halos. The JD's survey, with its spectroscopic confirmation of galaxy properties spanning redshifts from 4 to greater than 14, is providing the first observational map of this transition. By comparing the emission line properties of galaxies at different redshifts, researchers can track how the balance between ionized hydrogen emission and metal line emission evolves as a function of cosmic time, and in principle can identify the epoch and the environments in which the transition from population 3 to population 2 conditions occurred. The work is still in progress, and the systematic analysis of the full JDES spectroscopic sample at the highest redshifts will require several more years of data collection and analysis. But the early results suggest that the transition was already underway by Z equals 6, with galaxies at those redshifts showing a mix of very metal-poor and moderately metal-enriched spectral properties, and that the scatter in metal enrichment at a given redshift was large, consistent with the picture of an inhomogeneous transition proceeding at different rates in different environments. Roberto Maialino at the University of Cambridge, who's been involved in the JDES program and has published extensively on the properties of high redshift galaxies detected with James Webb, described the emerging picture in terms of what was unexpected. The standard models of galaxy formation had predicted that the most massive early galaxies would also be the most metal-enriched at a given redshift, because higher star formation rates would have produced more metals more quickly. The Webb data showed cases where this expectation broke down, where apparently massive and luminous early galaxies showed metal abundances substantially lower than their star formation rates would have predicted. Maialino and colleagues interpreted this as evidence for rapid assembly of stellar mass through population 3 and early population 2 star formation, in which the metals produced by stellar deaths had not yet been thoroughly mixed into the gas reservoir that subsequent generations of stars were drawing from, or in which the metals had been ejected from the galaxy by stellar feedback before they could be incorporated into new stars. Either way, the picture that emerged was of a more turbulent and less orderly chemical evolution, in the earliest galaxies than the standard models had assumed. The black hole connection to population 3 stars adds another dimension to the story. The most massive population 3 stars, those exceeding 260 solar masses, were predicted to collapse directly to black holes without producing significant metal ejection. Those black holes, formed within the first few 100 million years of the universe, would have been embedded in dense gas environments with high accretion rates, conditions favourable for rapid mass growth through gas accretion. If a significant fraction of the most massive population 3 stars collapsed to black holes in this way, they could in principle have provided the seed black holes from which the supermassive black holes at the centres of the most massive present-day galaxies eventually grew. The quasars observed at Z greater than 6, some of which harbour black holes of 1 billion solar masses or more, have long posed a challenge to models of black hole growth from stellar mass seeds, because growing a solar mass black hole to 1 billion solar masses in less than 1 billion years requires sustained near-Eddington accretion that is difficult to maintain continuously. Population 3 collapsed black holes, potentially ranging from hundreds to thousands of solar masses, provide a head start that substantially relaxes the growth constraint. The black holes now powering the most luminous quasars in the early universe may trace their lineage directly to the collapse of the most massive first stars, another thread in the causal chain that connects the first stellar ignitions to the large-scale structure of the universe today. There is a detail embedded in the spectroscopic data from JDs that is easy to overlook, but that carries implications extending far beyond the measurement itself. The oxygen abundance in galaxies at Z greater than 6, inferred from the ratio of oxygen emission lines to hydrogen emission lines in their spectra, is systematically lower than the oxygen abundance predicted for galaxies of the same stellar mass in the low redshift universe. This was expected in a general sense, because galaxies have been forming stars and enriching their gas for less time at high redshift than at low redshift. But the magnitude of the oxygen deficiency in the most extreme high redshift objects is greater than the standard galaxy evolution models predicted, and in the most metal-poor objects, the oxygen abundance falls into a range that is difficult to explain without invoking enrichment histories involving extremely low metallicity stellar populations at some point in the galaxy's formation history. Oxygen is made in massive stars, specifically in the helium-burning shells and the neon-burning cores of stars with initial masses above approximately 10 solar masses, and it is ejected into the interstellar medium by core collapse supernova. Population 3 stars, because of their extreme masses and their high stellar temperatures, were predicted to be prolific oxygen producers, and their pair instability supernova deaths were predicted to be among the most energetic oxygen ejection events in cosmic history, capable of distributing the products of oxygen synthesis across distances of hundreds of kiloparsecs in a single explosion. The oxygen abundance in the most metal-poor high redshift galaxies that jwst has detected may thus carry the direct chemical signature of population 3 pair instability supernovae, an enrichment pattern that has been predicted from theory for 2 decades, but that only now, with Webb's spectroscopic capabilities, can begin to be tested against actual observations of galaxies in the epoch when those events would have occurred. Takashi Moriya at the National Astronomical Observatory of Japan has published theoretical predictions for the pair instability supernova contribution to the chemical enrichment of the early universe, working with models of population 3 mass functions and population 3 stellar evolution codes to predict the distribution of element abundances expected in the gas enriched by pair instability events. The comparison of Moriya's predictions with the oxygen abundances and other elemental ratios emerging from the JD's spectroscopic catalogue is still in progress, and the results of that comparison will be among the most important constraints on the population 3 mass function, available from observational data. The mass function encodes the initial conditions of population 3 star formation, and the chemical yields of the first stellar generation, preserved in the abundance patterns of their enrichment products, are the most direct traceable record of those initial conditions available to observation. There is a deeper question lurking behind the oxygen measurement that is harder to answer with current data, but that the next decade of Webb observations may begin to address. The population 3 stars that enriched the earliest galaxies died before those galaxies had assembled much stellar mass in the subsequent population 2 generation. Their chemical products were incorporated into the next generation of stars, which themselves lived and died and enriched the gas further, in a chain of chemical evolution that has been running continuously since the first stellar ignitions. The most metal-poor halo stars in the Milky Way, those with iron abundances less than 10,000ths of the solar value, are thought to preserve the chemical composition of gas enriched by just one or a few population 3 supernova, and their element abundances contain information about those original explosions that has been preserved for 13 billion years in the photospheres of low-mass stars whose surface convection zones do not mix metals to any significant depth. The comparison between the chemical abundances of the most metal-poor halo stars in the Milky Way and the abundance patterns inferred for the earliest galaxies from James Webb spectroscopy is a comparison across 13 billion years of cosmic history and across a distance of tens of thousands of light-years on one hand and billions of light-years on the other. If the same population 3 enrichment signature appears in both the nearby halo stars and the distant high redshift galaxies, the case for a universal population 3 formation mechanism operating in similar ways across the earliest cosmic epoch becomes substantially stronger. The night sky, as seen from a dark site, carries information on multiple timescales simultaneously. The stars visible to the naked eye are mostly within a few hundred light-years of Earth, their light travelling for times ranging from a few years to a few thousand years before arriving at the eye. The smudge of the Andromeda Galaxy, just barely visible as an elongated blur on the darkest nights, is light that has been travelling for 2.5 million years, emitted by stars when our ancestors were only beginning to develop the stone tools of the Paleolithic. The faintest smudges visible in the Virgo cluster direction through binoculars are light that travelled for 55 million years, emitted when the last dinosaurs had been dead for only 10 million years, and the first primates were just beginning to differentiate from other mammals. And the light that James Webb is capturing from galaxies at Z equals 14 has been travelling for 13.5 billion years, emitted by the stars that formed and began their nuclear burning when the universe was less than 2% of its current age, before the Milky Way existed, before the solar system was assembled, before the chain of stellar evolution that would eventually produce the chemistry of life had run more than a small fraction of its course. The fact that this light is detectable at all is a consequence of two independent circumstances, each of which required specific conditions to obtain. The first is the existence and capabilities of the James Webb Space Telescope, which reflects, as noted earlier, the accumulated scientific and engineering effort of a civilization that itself owes its existence to the chemical legacy of earlier stellar generations. The second is the size and structure of the observable universe, which happens to place galaxies at Z equals 14 at apparent angular sizes and flux levels that fall within Webb's sensitivity range. Had the universe been expanding significantly faster, those galaxies would have been redshifted beyond Webb's wavelength range. Had they been significantly fainter, their spectra would have been undetectable at any reasonable integration time. The window in parameter space within which the first stars are observable by an instrument like Webb is narrow, and the fact that we sit inside that window reflects both the physical parameters of the universe and the specific capabilities of the instrument built to observe it. This convergence of circumstance is not mystical. It is the natural consequence of a universe whose parameters permit the existence of stars, which permit the existence of heavy elements, which permit the existence of rocky planets, which permit the existence of biological evolution, which permits the existence of technological civilizations capable of building observatories. The parameters of our universe are self-consistently related. A universe that permits observers also permits the observations those observers want to make, because both the observers and their instruments are products of the same physical processes operating across the same 13.8 billion years of cosmic history. James Webb's ability to detect the first stars is not a coincidence. It is an expression of the fact that the first stars made James Webb possible. The scientists working on this problem are aware of standing at a particular moment in the history of their field, a moment when a question that has been theoretical for decades is transitioning into an observational discipline. The transition is not complete. The definitive spectroscopic confirmation of population 3 star formation in individual galaxies remains ahead, dependent on integration times and observing programs that are already planned and already partially underway. But the direction is clear, the evidence is accumulating in a consistent direction, and the instruments are in place to complete the observational program. When the confirmation arrives, as most researchers in the field expect it to, it will represent the completion of a scientific story that began with the theoretical prediction of an unobservable class of stars, developed through decades of numerical simulation and indirect observational inference, and arrived at direct detection through the construction and operation of the most sensitive infrared telescope humanity has ever placed in space. That is not merely the end of a scientific story, it is the beginning of a new one, because every confirmed detection of population 3 enrichment in a high redshift galaxy opens new questions about the spatial and temporal distribution of the first stellar generation, about the mass function of those stars, about the efficiency of metal transport from the first supernova sites into the surrounding intergalactic medium, and about the timescale over which the transition from population 3 to population 2 conditions occurred in different environments. The questions that James Webb's Population 3 program will leave unanswered are not the same as the questions it was designed to address, and the instruments that will be needed to address those new questions have not yet been designed. The universe rewards sustained curiosity with progressively deeper mystery, and the first stars are no exception. What the James Webb Space Telescope has accomplished in its first 3 years of science operations is, by any reasonable measure, the most dramatic expansion of the observational frontier of astronomy since the construction of the Hubble Space Telescope. It has detected galaxies at redshifts exceeding 14, corresponding to epochs less than 300 million years after the Big Bang. It has obtained spectroscopic confirmations of galaxy properties at redshifts that were purely photometric estimates before its launch. It has revealed the chemical compositions of the earliest observable stellar populations through emission line diagnostics that no previous instrument could reach at those redshifts. It has found evidence for the influence of population 3 stars in the spectra of high redshift galaxies, a measurement that was purely theoretical for more than 3 decades before the telescope's data arrived. And it has produced, in the Cosmos Web Mosaic and the jwst spectroscopic catalogue, scientific data sets of sufficient depth and breadth that researchers who had nothing to do with the original observations are now using them to answer questions that the survey's designers did not anticipate. All of this represents the first chapter of a program that will run for decades. The telescope has enough fuel and shows no signs of hardware degradation that would limit its operational lifetime to less than the 20-year goal set by its designers. The observing programs already approved for its upcoming cycles include deeper spectroscopic integrations of the most extreme high redshift candidates, wider area surveys designed to build statistical samples large enough for population analyses at z greater than 10, and targeted programs designed to study in detail the properties of specific objects whose discovery in the first cycle data raised questions that the discovery observations could not answer. The scientific return from those programs will continue to arrive in the form of papers, conference presentations, and public data releases for years after this documentary is complete. And the story it will tell will be richer and more detailed than anything available today. The researchers who built the telescope and who are now using it to study the first stars are not merely answering old questions. They are building the foundation on which the next generation of astronomical instruments will stand. The extremely large telescopes currently under construction, including the extremely large telescope being built by the European Southern Observatory on Cerro Armazones in Chile, and the 30-meter telescope and the Giant Magellan telescope planned for sites in Hawaii and Chile, will combine the collecting area of primary mirrors 30 to 40 meters across with adaptive optic systems that correct for atmospheric turbulence to deliver image quality comparable to space-based observations. Those instruments will be able to obtain spectra of the most extreme high redshift objects discovered by James Webb at spectral resolutions and signal-to-noise ratios that the Space Telescope cannot achieve, providing the chemical abundance measurements and the kinematic information needed to characterize population 3 enrichment at the level of detail that turns indication into confirmation. The Space Telescope Science Institute, the Scuola Normale Superiore, the University of Texas at Austin, the University of Cambridge, the Max Planck Institute for Astronomy, and dozens of other institutions are actively planning the observational programs that will complete the population 3 story over the next decade. The universe does not care whether we understand it. The first stars ignited, burned, and died on a schedule determined entirely by the physics of primordial gas collapse and nuclear fusion, with no awareness of the observers who would eventually arise from their chemical legacy and peer back across 13 billion years of cosmic history trying to find them. That we have found them, provisionally and incompletely but genuinely, is entirely a human achievement, the product of curiosity sustained across generations, mathematical frameworks developed over centuries, engineering ingenuity applied across decades, and the specific capabilities of an instrument that was conceived before most of the scientists now using it had begun their careers. The first stars did not know they were waiting to be discovered. We did not know we were their descendants. Both facts became clear through the same process of sustained inquiry that defines science at its best. The light from jwst Z140 left its source 13.5 billion years ago, when the universe was 290 million years old and the first stars were still in the early phases of enriching the cosmos with the metals they were forging in their interiors. That light crossed the full observable diameter of the universe's history, was stretched by the expansion of space until it fell in the near-infrared, passed through the aperture of a 6.5 meter mirror, assembled from elements produced in the Big Bang and in stellar deaths distributed across billions of years of cosmic history, was dispersed by a spectrograph built from the same elements, and fell on a silicon detector array whose photovoltaic response converted the ancient photons into electrical signals that travelled at the speed of light through circuits assembled by engineers working in laboratories on a planet that did not exist when the light began its journey. The scientists who read those signals and recognised in the resulting spectrum the signature of the most metal-poor stellar populations accessible to current observation were not outside the story. They were its most recent chapter. We are the universe that looked at itself and recognised the moment of its own first breath. That recognition, incomplete and provisional and surrounded by honest uncertainty as it is the most remarkable thing that has happened in this field since the Hubble Space Telescope first showed that the darkness was full of galaxies. The first stars are there, their light, transformed and reddened and attenuated across 13.5 billion years, has been reaching us. We have finally built the instrument capable of reading what it says. The light from the first stars was not the only thing they contributed to the universe. Every photon they produced was accompanied by a gravitational influence, a perturbation to the matter distribution around them that propagated at the speed of gravity and affected the subsequent assembly of the structures into which the matter around them would eventually collapse. the radiation pressure from the first stellar radiation fields pushed the gas surrounding the first halos outward, in some cases suppressing star formation in neighbouring halos by heating their gas above the threshold for gravitational collapse. The supernovae that ended the first stellar lifetimes injected not just metals and energy, but momentum into the surrounding medium, driving galactic winds that could in some cases expel enriched gas from the shallowest dark matter halos entirely, distributing the chemical products of the first stellar generation across much larger volumes than the halos themselves occupied. The population 3 stars were not passive producers of radiation and metals. They were active agents in reshaping the structure of the early universe, their influence extending far beyond their own formation sites through radiative, chemical, and mechanical feedback processes that continue to be modelled and studied in detail. Claude McKee at the University of California, Berkeley, working with Jonathan Tan at the University of Florida, developed influential theoretical models of massive star formation from turbulent gas cores that, when extended to the primordial case, predicted population 3 stellar masses substantially higher than those typical of modern star formation. Their framework showed that the absence of dust and molecular cooling in the primordial medium removed the primary mass regulators present in contemporary star-forming regions, producing a first stellar generation whose mechanical and radiative feedback on the surrounding gas exceeded anything the universe has produced since. A single massive population 3 star could potentially clear all the gas from its host halo through radiation pressure and supernova ejecta, leaving behind an evacuated region in which the next generation of star formation had to wait until the surrounding gas cooled, fell back, and reached the density threshold for renewed collapse. This episodic feedback picture, in which star formation in the smallest early halos was intermittent and explosive rather than sustained and orderly, is substantially different from the continuous star formation histories assumed in the simplest galaxy evolution models, and it has implications for the interpretation of the emission line properties of high redshift galaxies that the jwst team is actively incorporating into their analysis framework. The connection between population 3 feedback and the large-scale structure of the cosmic web is more indirect but equally significant. The metals ejected by the population 3 supernovae into the intergalactic medium did not simply drift uniformly through space. They followed the density field of the underlying dark matter distribution, preferentially enriching the filaments of the cosmic web that concentrated gas in the protocluster environments where the first halos were densest. The result was a spatially inhomogeneous distribution of intergalactic metallicity at the end of the population 3 epoch, with enriched filaments and halos surrounded by voids of nearly pristine primordial gas. Some of those pristine voids may persist today as pockets of extremely metal-poor gas in the intergalactic medium, and some of the most metal-poor damped Lyman alpha absorbers detected in quasar spectra may represent reservoirs of gas that have retained a significant fraction of their primordial composition despite 13 billion years of surrounding chemical evolution. If so, the intergalactic medium itself, the thin gas between galaxies that fast radio bursts probe through their dispersion measures, carries the record of population 3 feedback distributed across the full volume of the observable universe, a chemical fossil of the first stellar generation written in the trace metal content of the space between galaxies. Xavier Prochaska at the University of California, Santa Cruz has spent years analysing the metal content of intergalactic gas through the absorption features it produces in quasar spectra. The most metal-poor absorbers in his surveys fall at column densities and metal abundances consistent with material that has been enriched very slightly by just 1 or 2 supernova events from a completely pristine primordial composition. Some of these systems may represent gas in the outskirts of early halos that received a single population 3 supernova's worth of metals and has not been substantially further enriched in the 13 billion years since. others may trace the enriched outflows from population 3 host halos that propagated into the surrounding intergalactic medium before the reionization era was complete. Distinguishing between these possibilities requires the combination of quasar spectroscopy and galaxy survey data that the James Webb Telescope is now beginning to provide, as the counterpart galaxies of the most metal-poor absorbers are identified for the first time at the redshifts where the JD's spectroscopic catalogue provides the most complete census of the galaxy population. The story of the first stars is, at its core, a story about beginnings, and beginnings have a particular quality in science that distinguishes them from other kinds of discovery. When an observation confirms a prediction that has existed in the theoretical literature for decades, the confirmation is significant not merely because it validates the theoretical framework, but because it closes the loop between the model and the reality the model was designed to describe. The prediction that very massive metal-free stars would form in the first dark matter halos of the early universe was made on the basis of physical reasoning from first principles. The observation that the spectral properties of the earliest accessible galaxies bear the signatures of those stars validates not just the specific prediction, but the entire chain of reasoning from the Big Bang nucleosynthesis, through the formation of dark matter halos, through the collapse of primordial gas, to the first stellar ignitions. Each link in that chain has been independently tested and confirmed, but the confirmation of the final link, the actual existence of population 3 stars as evidenced by their chemical influence on the earliest observable galaxies, gives the entire framework a coherence and a completeness that it could not have before. We have gone from a universe in which the first stars were an untested theoretical prediction to a universe in which their influence is being read directly from the spectra of galaxies that formed when the cosmos was less than 3% of its current age. That transition happened in less than 4 years of science operations with a single instrument. The implications for what becomes accessible in the next 20 years, with Webb continuing to operate and the next generation of extremely large ground-based telescopes beginning to produce data, are genuinely difficult to anticipate. The history of astronomy suggests that every new generation of instruments finds things that the previous generation could not have predicted, because the universe is more complex, more varied, and more surprising than any model built from previously available data. James Webb has already demonstrated this principle with its discoveries of impossibly massive early galaxies, its confirmation of the reionization history through Gunn-Peterson measurements of faint ZZ greater than 7 quasars, its chemical characterization of the most distant spectroscopically confirmed objects in human history, and its evidence for the population 3 stellar generation that made everything possible. What it will find in its remaining operational years, and what the instruments that follow it will find in the decades after, is, by the nature of frontier science, impossible to specify in advance. The only certainty is that the universe will continue to be more than we expected. Hold your hand open in the dark one more time. The atoms that compose your hand were assembled in the interior of a star, scattered by its death, gathered by a gravity over hundreds of millions of years, incorporated into the molecular cloud from which the solar system condensed, deposited on the surface of the Earth over 4.6 billion years of geological and biological evolution, and assembled into the specific arrangement that constitutes your hand through the continuous metabolic activity of the living system you inhabit. Every one of those steps depended on a prior step, and the chain traces back without interruption to the moment when the first stars ignited in the cosmic dark ages and began converting the universe's primordial hydrogen into everything else. The darkness that preceded the first light was not empty. It was full of the potential that those first ignitions would realize, and the light that James Webb is now collecting from the earliest observable galaxies is, in the most literal physical sense, available to the language of science, the light of our own most ancient origin, travelling toward us across 13.5 billion years of cosmic history, arriving at instruments built from its own legacy to be read by minds that the same chain of events eventually produced. The 20 years of operational life that engineers designed into the James Webb Space Telescope represent a commitment to sustained inquiry of a kind that is itself a product of the chain of events the first stars set in motion. The observations conducted in the telescope's first 3 years are a small fraction of the scientific program that will unfold across its full operational life. The spectroscopic programs already running will return higher signal-to-noise data on the most extreme high-redshift candidates. The statistical samples needed to determine the population 3 mass function from observational evidence, rather than theoretical inference, will accumulate year by year from the JD's survey and its successors. The moment of unambiguous, definitively confirmed, alternative explanation, excluded direct detection of population 3 star formation in an individual high redshift galaxy has not yet arrived. It is coming. The instruments are in place, the programs are running, and when that confirmation arrives, it will represent the completion of a scientific story that began with a theoretical prediction made before most of the scientists who will publish the confirmation result had begun their careers. The practical implications of this work reach beyond astrophysics into the deepest questions about what the universe permits to exist. The abundance and distribution of heavy elements in the early cosmos set the initial conditions for everything that followed. Rocky planets, liquid water, carbon chemistry, biological molecules, the long sequence of molecular and cellular and organismal evolution that produced technological civilization on at least one world. All of it depended on the prior distribution of metals from stellar deaths into the gas from which subsequent generations of stars and planets formed. The population 3 epoch was the first chapter of that distribution. How efficiently it enriched different regions of the early universe, how rapidly it enabled the transition to conditions suitable for rocky planet formation, and how uniformly or inhomogeneously it distributed. The first metals across the cosmic volume are questions whose answers will eventually bear on the question of how common the conditions for life are across the observable universe. James Webb is beginning to answer them. Hold your hand open in the dark one more time. The atoms of your hand were assembled in stellar interiors over billions of years, scattered by supernova deaths into the interstellar medium, gathered by gravity over hundreds of millions of years into the molecular cloud that collapsed to form the solar system, deposited on Earth through geological and biological processes spanning 4.6 billion years, and assembled into the specific arrangement that constitutes your hand through the continuous metabolic activity of the living system you inhabit. Every one of those steps depended on the one before it, and the chain traces back without interruption to the first stars that ignited in the cosmic dark ages and began converting the universe's primordial hydrogen into everything else. The iron in your blood is their legacy. The calcium in your bones is their gift. The oxygen your lungs are drawing in carries the chemical signature of the stellar furnaces they became. James Webb is now detecting the light of the galaxies those first stars inhabited. Light that has been travelling for 13.5 billion years, stretching and dimming across the full span of observable cosmic history, arriving at a mirror made of beryllium and coated in gold whose atoms passed through stellar deaths of their own, before being assembled by engineers working in laboratories on a planet those first stars helped make possible. The telescope is composed of the first star's legacy, pointed at the first star's light, operated by minds assembled from the first star's elements, asking the deepest question those minds can form about their own ultimate origin. That is not a poetic sentiment. It is a precise physical description of the situation. We are not outside the universe examining something foreign. We are the universe that learned to examine itself. And the first stars whose light James Webb is now finally reading after 13.5 billion years of travel and not something we found out there in the distant past. They are what we are made of, looking back at the moment they began.